Are we there already?
I think so.
Okay, so we are live now. Hello, everyone. Good morning, good afternoon, maybe even good evening. On our next and most probably the last international webinar in this year. And it's almost Christmas special webinar dedicated to stability issues, stability problems, buckling safety. So as you will see, we try to compare our hand calculations with IDEA StatiCa solutions. And who's here today for you? You are lucky because you have probably the most serious product engineers from the company here. Me, myself, Jan Kubíček, and Adam Kozoušek, another product engineers dedicated mostly for steel. Adam, are you here somewhere?
I hope so. Hope you can see me as well. Greetings, ladies and gentlemen, dear engineers. I see that you behaved well. So you have this pre-Christmas present of this webinar today. It's a pleasure to have you here. I am today's the Santa Yanko little helper, and I will guide you through the presentation and the examples today. So welcome.
Thank you, Adam. Little helper that will do the most of the heavy lifting today. Okay, as usual, we are broadcasting through GoToWebinar platform. You can use the question panel for asking the questions through our presentation, and we try to answer everything immediately. Or if we can't manage everything, you will get the answers to your email inboxes tomorrow or today. And yeah, if you can't see all the options in the platform, you can use this palette at the left side. And today's topic, as I mentioned, so stability of members. We try to show you that sometimes even the very simple ones, the simple members, simple situations could be crucial, could be critical when they are influenced by specific details. Okay, and yeah, as we always do, we are very keen to see or hear your feedback, your point of view on the topic. So we prepare several polls, and the first one is dedicated to general question: how do you assess this kind of stability calculation? So the options are hand calculations, global model in FEA software, or IDEA StatiCa Member, or any other solution. So I'm launching the poll now, and please select your favorite option.
All right. The voting is in progress. Janko, what is your experience? You worked as a structure engineer before IDEA StatiCa, so you are actually very experienced and skilled structure engineer. What did you do in your practice?
In most of the cases, I try to find the most simple solution and explanation. So if it's on me, I would prefer the situations with simple buckling lengths. But if it's more complex, I would use a global analysis software and try to solve the calculations there. Or in the most complex situations, I would use some hand calculations, very time consuming. Unfortunately, I didn't know about the member application these days.
Yes, I see. And no structure has fallen.
Yeah, happily, fortunately, not yet.
So you were on the safe side. Did you feel that you would maybe sometimes overkill a structure using these hand calculations or kind of estimations with the global model?
Yes, I think I overkilled something previously just because I didn't have enough information about how it will be built. So I over-designed something. And I can see the voting is probably over, so I'm closing it now and showing the results. So as you can see, yeah, the winner is the B option, global model in FEA software. So it's probably quite similar to my approach, and if you don't have everything there, you will use hand calculations. Only 8% would use IDEA StatiCa Member. That's good. That's why we are here, and that's why we show you why this number should rise quite soon.
Of course. All right, we can close the poll and the survey. Thank you for your answers. And so I will now take over the presenter and show you my screen. And I will now start with my part of heavy lifting. So I have prepared for you a example. This is a real example from one European country, but for let's say understandable reasons, I want to keep it anonymous, and we will just keep this in our minds, and I'll guide you through the whole process of how this segment of a structure was designed, calculated, also checked for stability, and we will redo the process and see the outcomes and see possibilities and so on. So this is the segment of the structure. It's a very simple one, just a column and a beam laying on top of this column on an end plate with side bracings stabilizing the beam. This is in the middle of a wholesome steel structure. You can see that the rest of the structure around has a kind of a stiffening of fields and so on. So, and this is this beam covers kind of a hole below, so like a wider space, and on top of that beam there is a continuing structure, so there's a load on that. So we have a picture of where we are and what are we dealing with. So now I show you the parameters of this structural segment we are looking at today. So the column 6 meters high section is HEA 300, steel 355. So this is a European structure solved under Eurocode. The beam 8 meters long, IP 500, and there's a line load of 250 kilonewtons per meter. So quite a big load that needs to be transferred to the anchoring and to the surrounding structure. And the bracing members, those are hollow sections 80 by 80 by 5 millimeters of thickness, 10 meters long. So this is it. So this is now on our table, as we are the structure engineer to deal with this. And I'll show you what was the first step and what would be also my first step. So do the, let's say, global model of this segment of the structure in FEA software, calculate there for the limit states and also for the stability assessment. So I'll jump out of the presentation and open my FEA software. This model was calculated and modeled in SIA Engineer, one of the FEA solutions, very similar to SAP 2000, ETABS, Bentley, robot, or whatever you like and use. So this is one of them. And as you can see, this model is quite simple. I have the column here, the beam, the bracings. You see that everything is in the correct position. What is the most important thing is probably the supports. So as we can see, the bottom of this column is fully rigid, so it's a fixed support. The anchoring was designed to be quite stiff with a thick base plate and a bigger anchors, so very strong one, so we can easily suggest a fixed support. For the main beam, IP500, the supports here at the ends are pinned with a restraint of rotation around x-axis. So I believe we agree this is correct with respect to the surrounding structure. And these bracings, since they are connected by a pinned connection, they are small, so there is possibly some rotation as well. This is a full pin, so a hinge connection. All right, so if I calculate this model now, a linear calculation, so it gives me the limit states as I can navigate here and see quickly just the overview. So I can see the section check. So this is the utilization in that, as well as we can go through the stability check here. And we can see basically utilization factor, also other results. So here what I want to show you is that the checks are just showing this is all okay. You can see the utilization factor with the stability check is around 30% of utilization for the column and about 40% of it for the beam in the field, and 54% of the capacity is used for stability above the connection. All right, so I can conclude that using the FEA software, the global model, I calculated the limit states and the stability with the linear calculation. It's a simple model, a simple method was used, everything is correct, and I passed the checks. So everything is fine here. So I can close this, conclude the job is done, and I jump back to the presentation. And the second thing I do, and the original engineer did as well, was a, let's say, second calculation to make sure that the stability was assessed correctly. So I use the hand calculation following the code equations and procedures. So for buckling, this is, well, both of them are quite easy. The buckling of column, it's a pure compression, so quite a simple procedure. For the beam, it's pure lateral torsional buckling from the bending moment only, so also quite a simplified procedure to follow. So I will show you all these equations and the handed out paper. And before that, I have another quick poll for you, or a little quiz prepared. So get your brains and experience ready, please. This is the quiz. So you saw the structure, you saw the system, and now as you need to do the hand calculation, you need to determine what is the static scheme of the column you want to analyze for buckling to determine the buckling length and the critical length, right? So you need to choose from the static schemes, and from the static schemes as per Eurocode, you obtain the value of beta that you use for the equation. So Janko, can you please start voting?
Yes, it should be there.
All right, the voting is in progress, as I can see. That's cool. So what about you, my Santa?
What about me? You mean what
What
would
is
I
your
choose?
yes, what's your opinion on this?
Yes, my opinion is that the closest has to be for sure the option B. Why not? Yeah, the anchored base plate and not that rigid end of the column. So maybe not exactly 0.7, but that's probably the closest one, isn't it?
Yeah, and it's also one of the options the code gives you. So there is not really much maneuvering space around this. You either choose that one or another one, nothing in between, right? Or you need to somehow estimate.
Correct. But which way? Down or up? Closer to 1, closer to 0.5? Who knows?
Yeah. All right, we will know in a minute.
That's why you are doing it in Member. Okay, makes sense.
Right. Okay, I think we can close the voting. Most of the people has finished.
We have the results.
All right. So you see, or I see that you are also, you are probably right. You're sharing the same opinion as almost 70% of our attendees. So thank you once again for voting in this survey or in this poll. And I will continue with the presentation. So let's close the results. And actually that's the same conclusion of mine and also the structural engineer that did the original calculations and design. So this is logically looks like the most fitting scheme to pick, right? Quite makes sense. So, all right. Sorry, that's one slide ahead. I'm going to jump out of the presentation and show you the hand calculation. So this is another tool that I use. It's the MathCAD, similar thing to Excel. You would mind. This just looks nicer. That shows you the equations and the mathematical signs and everything. So you can produce a nice report out of this. Still, it's quite a simple tool. But so let's see about the solution. So here I summed up the inputs, the parameters of the cross section and the column. So the length 6 meters, cross sections and the cross-sectional parameters here. The compression force as calculated from the global model is 1,200 kilonewtons. So this is a centric compression in the axis of the column, so no eccentricities, all symmetrical and centroid. And the steel parameters, of course, Young's modulus and so on. Very easy to obtain from the tabs. All right, so now how to follow this hand calculation. So you, as we are in Europe, we use Eurocode for this. So you follow the procedure. Eurocode 1993-11. It's the clue or the chapter 5 and 6. There you find the equation for the critical length. Here you use the previously determined factor B as 0.7 and calculate the buckling length. I did this for both of the say axes or planes. So the weak axis and the strong axis of the I section of the column, of course, to make sure I don't neglect something. So, all right, so we continue determining the parameters that are needed for the further calculations. That's very simple procedure. Then you find this tab where you find the appropriate buckling curves. From this tab, you go to other tab where you find the imperfection factor alpha based on determination of the buckling curve type. And you use these values for the calculations of other factors. All right, so it's a couple of equations that actually doesn't tell us a lot, but we obtain some numbers. And finally, we use this equation to obtain the resistant force, which is 3,600 kilonewtons. Compare it to the acting force, and we see that finally the utilization is around 30% for this plane and 43% for the plane perpendicular to Z direction, Z axis of the column. So this was very easy. We have the results. We see that we passed the checks for stability of this column. The utilization is around 40% maximum, so everything is just fine. And it is in accordance to our global model in the FEA software, right? There we passed the checks as well, around the same utilization. So like a double proof that we are fine. Very similar thing is for the lateral torsional buckling of the beam. Again, one-page calculation. This is symmetrical, simple problem. So the whole procedure can be simplified so much that it just fits one page, right? So this is like a university example or school example, even I would say. But let's see what we have here. The beam, 7 meters long, cross-sectional parameters, all listed here. Parameters of steel listed here. The G modulus derived as well, and so on. So these are the inputs here. For the beam, we also need to determine, based on the code offer, let's say, what the code offers in the tabs and in the options. Choose the static scheme. So we will be dealing with the lateral-torsional buckling of the beam in field, since there, of course, it's more dangerous. So the buckling factor for determining the critical length is the beta is 0.5 in this case, and the design bending moment as read from the global model analysis is 330 kilonewton meters. So again, what we do is we follow the Eurocode procedure, go to the tab in chapter 6 and determine the buckling curve type or class, it's B. Then we determine the imperfection factor alpha LT, lateral torsion, from another tab. And again, we follow the equations that are proposed in the code. So the buckling length is half of the length of the beam, and then we calculate the critical moment and other factors that just gives us some numbers, right? So we just input the parameters and we end up with the resisting moment resisting towards the stability, which is about 500 kilonewton meters, compared with the acting moment. This uses about 66% of capacity of this beam. So again, we check the beam as per stability. Everything is fine. Double checked by hand calculation. So I can easily end this job, deliver the report, and I'm fine as a structure engineer with this. All right. Now back to the presentation. So we did the FEA analysis, we did the hand calculation. What's left is the connection design. This was done in IDEA StatiCa connection app. So let's see the model. This is it. So we can see the column, the beam. The connection between the column and the beam is an end plate operation. The design is the thickness of the plate is 10 millimeters. There are M20 bolts used, standard bolts of grade 8.8. This is welded by 6 millimeters weld. And the setup is like this. From the other side, it's just the same. All right. The connection of the bracings is again symmetrical end plate, 10 millimeters of a plate, smaller bolt, and that's it. So this is very standard design, nothing special. The load here, the internal forces that has been derived from the global model again, the same compression force in the column and shear forces and moments in the beam, as well as some small forces in the bracings. All right, so if I calculate this, I run the analysis in connection. The first picture I see is that everything is green or gray, all the green marks, so everything is fine. So what I can do is just do little dig into the results and see what's the plastic strain, if there's any. There's some plastic strain in the welds, and I can see the deformation trend just to make sure that my model works fine, and obviously this does. So see the stress distribution. All right, of course we have the stress peaks where the bending happens of the beam. So this is just very fine. You can see the bracings are not very used or utilized. They are there purely for stabilization of the beam, so it doesn't fall over, right? What I can do as well is calculate the local buckling or the buckling in this connection. So let's see what it shows us. This is a very good thing to do always, to see any potential hazard of buckling revealed in the connection analysis. So I will display the buckling shape. I will lower the scale and see about the result. So this is a first buckling shape. We can see some buckling in the web of the main beam. The factor value 3.87. So the question is this safe or not? The answer is this is considered to be safe. So I can show you also, if you are interested to get more information, you can always use this help field. Just write or type there some keyword, press enter, and your browser with navigation to our support center webpage opens. You can see some articles discussing these things. So this is about buckling. So the local buckling of plates or panels, as we can see, what is in case about 3-4 is considered to be safe in this case. So, all right, I've done everything I should have done, and I'm fine. So let's say the job is done. I finished my work as a structure engineer, delivered the reports, and now the construction just happened. But until now, I hope we are all on the same page and we see that this is nothing special. It's rather a boring thing, but probably you already smell some some issue there, and there was, of course. And the issue was that basically this segment collapsed. It was constructed, it was loaded, and collapsed. It was not a big tragedy, but still it happens. So the question is why? What happened? Since our design was okay, we did everything we had to, and still. So first thing that you would take a look is at the construction site, if there's something wrong, as the workers or the company on the side did some error or something wrong. That was not the case. Everything was as per the project. So let's see now, and this is also what happened when the and there were the let's say a group of engineers or the external agency did the research of the problem. And what they did, they used IDEA StatiCa Member, build a model there, and see to see what possibly could happen. So I will now show you the IDEA StatiCa Member app with the finished model. So this is it, and we can see what's there. So in IDEA StatiCa Member, what you actually do is that you input a one or multiple members. In this case, it's the member, is the column, as analyze member. And for this one, this is the main member that's going to be analyzed by geometrically nonlinear analysis with imperfections. So the most advanced analysis for assessment of stability in a software. So let's see about the model. Here I have the column. As you can see there, I have the beam, the IP 500, the bracings, the same connection modeled as you saw in the previous connection model. I have the supports. So let's see, on the base of the column, I can even open and edit the connection. There you can see the designed anchoring. So let's see some details of it. So if I click on this edit connection, IDEA StatiCa connection app opens, and this way I basically create or add the design of the connection. So you all probably know this app, right? How it works. So I can only like revise this operation of a base plate. So that's nothing special. Just I want to show you that this anchoring is very, very strong with a thick base plate of 30 millimeters and the long anchors with washer plates and so on. So this can be on a first sight considered to be a fixed connection or fixed support, right? Of course, I could do any modifications anytime, but I want to leave this design as original. The same thing is here with the connection of the column and the beam and bracings. Here, the same design was used as for the connection design, connection calculation. So there is nothing more to show. What else are the supports at the ends of these related members? So these are the same, that's the same setup and as in the FEA model. So again, pin support with restraint of torsion around the x-axis, the same on the other side, and fully pinned connection or a nodal support at the end of the bracings. All right, and there's the load, the line load of 250 kilonewton per meters. All right, so to assembly this model, it's very easy. So I just even skip this to save time of our webinar today. So I'll proceed to the analysis. The analysis in IDEA StatiCa Member is done in 3 steps. First, you calculate the MNA, materially nonlinear analysis, which is geometrically linear. So this is the very same analysis as in any FEA software. So the same thing that SAP 2000 or a robot or CI Engineer or whatever you use shows you. Yeah, just that the difference is this is in shell, this is with shell elements, with 2D elements. But this is honestly nothing special. It shows you the check of sections and of plates and compares it with the 5% of strain criteria. But if you would read these results and compare it to your global model, this will be pretty much similar. Second step, this is more interesting. This is the linear buckling analysis, LBA. So this type of analysis calculates possible losses of stability, possible buckling shapes, and also shows you the buckling factors. All right, so I can see the first buckling shape. I can also overscale it. So it looks like this and already gives us some idea what's the problem with this detail, this part of the structure. Also the factor, which is 1.44, is quite low, so it also shows potential hazard, right? I can also see the other buckling shapes. This is a local buckling of the web of the beam. This might be also potentially dangerous since the factor is also quite low. And these are more buckling shapes. And by checking them and considering them, we can basically say this would not happen at the same time as the first one. So the first one usually is the most dangerous and the one that could happen. Second one, sometimes if it's a local buckling, can happen together with the first one. So we take these first two buckling shapes into consideration for the third analysis, which is the geometrically nonlinear analysis. So second order analysis with imperfections, with stiffness of the connections incorporated, as well, of course, of the buckling shapes taking into account. Right, and before we run the third step, the geometrically nonlinear analysis, we want to input the imperfections. These imperfections are represented by the value in millimeters. And again, if you are not sure, just type in the word and see the articles. So here I can read how to input the imperfections in Member. This is very easy. For Eurocode and American code, other codes, very similar. Basically just one tab or one equation where, based on the length of the beam and the buckling curve, you determine the imperfection value. For the local buckling, it's other tab. Again, very simple. Just divide the beam web height by 200, and that's it. So if I jump back, so the input is 24 millimeters for this global buckling shape and 2 millimeters for the local buckling of the web. All right, and I push the calculate button of this most advanced analysis that you can have nowadays in the software. This is similar that if you would compose such a model in, for example, ANSYS or Abacus and input all the settings, there it would take you probably some couple of hours. Here you do this in minutes, but enough of showing off. I want to show you rather the results. You can see now the calculation takes rather longer time. This is because there is something happening. So there is plastification occurring. So the solver is trying to find the final state. So this calculation takes about a minute. So to skip the waiting, I have the same model here already calculated. We can then jump back to the original one. But anyways, I don't want to keep you waiting. This is the results, and we can see basically what happened with the structure and what's the problem. So the problem is that the column buckled and the beam just fell over. You can see the critical point is in the web of the beam, and you can see that with 88% of the load applied, this structural segment lost its stability. So we found the problem, we identified what happened with the structure. Now we can think only why, and I guess most of you already know the reason. If I go back to this display, so the reason is, and that's our today's lesson, that the web of the column is quite high, right? And the bracing is located on the top of the web of the beam. So it is stabilizing the beam, but in its upper part. But the lower part, with combination of this high web, with combination of this rather weak connection, it basically creates another intermediate hinge around here, in where the beam and the column can deform, rotate, and kind of a bend. So this is what happens. So we not only, with using IDEA StatiCa Member, identified the problem during the design phase, but also we see the behavior of the structure and we can react on that as a structure engineer. So we have a full picture of what's happening and we can prevent the hazard. That's cool. So if I jump back to the presentation and sum up this and see what was the problem we did, or I did, and the structure engineer calculating this did, was the assumption of the static scheme. So because the detail was designed as it was, it's not this this type, but it's rather something like this. So there's like a hinge, a virtual hinge in between, and the factor for calculating the critical length is not 0.7 but something around 1.7. So if I would now repeat the hand calculation with this factor, I will end up with a failing code check also in the hand calculation, right? So the hand calculation is not, the procedure is not bad itself, it's just the assumptions that we bring into it, right? Also, it has limitations, but in this case, that's not a problem. All right, so we know the problem, we know the reason, we learned the lesson here, and why did it happen? The reasons were probably, as is usual, multiple. So one reason was just to inform you that the structure engineer was rather junior. There were also some architectural let's say demands on the detail. So they asked him to leave out the stiffness there. Also, the design was handled to another let's say persona in the process, so on. So some information was lost. So these things just happen, and it happened here, unfortunately, but it was not very a big tragedy. So the structure was simply repaired and the connection stiffened. We can see how it behaves, or how to do that in Member as well. So I can go back to the original model that I finished the calculation. In the meantime, of course, I have the same result. So I go back to design and see what happens if I edit this connection and add these stiffeners. So I open the connection app, and I would want to add a stiffen operation as it was done on site and in the revision of the project, right? So this is the connection model. So I add the stiffener operation and put it on the rear only. So it still kind of fulfills the architectural demands. So just save it. Oops, I've got an error here. Some data was mixed with my other model here, since I have two opened at the same time in the same folder. That's probably the reason. So let's just repeat this in this other window. So I just quickly do the same. and then we recalculate the member model. All right, stiffener, rear, A, let's see, and this is going to be RM6, right? Let's save this, and stiffener is there, so let's go to check and calculate the first the materially nonlinear analysis. Here we obtained a very similar results as the original design, and I switch to linear buckling analysis. Oh, the calculation window is shown on my second screen, so you don't see the percentage raising, just the results. And already here with the linear buckling analysis, we can see that the first shape, if you remember, it looks very different. It now looks more or less corresponding to the static scheme we would choose the first. So fixed support here, pinned here, there is some bending of the column, and this detail works nicely together, the beam and the column. Also, the factor, instead of 1.3 it's 5.5, which is quite high and quite safe. So if I calculate the geometrically nonlinear analysis, I use the same imperfection values because the imperfections are based on the geometrical properties of the beams. And this is done, and I can see the results. Now, I passed the code checks. I see no problem here. Everything is green. I can see the deformation. If I overscale it, it just works as expected. So the output, the results I have, they are very simple. Basically, everything is considered in the analysis, and what I can check is simply the 5% of strain criteria. That's all. So I don't care of any buckling lengths, any factors of anything like that. Everything is inside. So I only see the very, very simple output. And this is, of course, as per code. So that's basically it for the demonstration. So if I sum it up and point out the lesson learned today. So the analytical approach, which was used in the FEA software, the stability there, as well with the hand calculation, is, as we see, usually a simplification of the problem. And there is a potential hazard of some misunderstanding. So it can lead to a mistake in the design and analysis. That's something to keep in mind. Another lesson learned is that small details like one stiffener in the structure can be critical. One stiffener in one beam can be a critical thing for the whole structure, or at least a segment of it, right? So that's, for me at least, that was very good lesson to learn. And the last thing to emphasize here, if you see such a detail with a high or tall web, even though it has bracings, always think twice and be careful and don't design such details without stiffener. or IDEA StatiCa Member to make sure you pass. And this is also conclusion of the expert team that was analyzing and researching the problem, doing the calculations. I like this. This is an email from one of the members of the team. I like this sentence that they were discussing the conclusions of the analysis with the on the construction site, and so there was some disagreement, some negotiation, some argument. But this guy says, I explained that, and the misfortune of these people was that the choice of their design or how they did it was just laying on the ground. So it's a funny and a little sad thing at the same time, but that was a good lesson. All right, so we are coming to an end of this webinar. So we have a last poll for you. So Janko, you ready to run this poll?
Yes, I am. I just was muted.
I can hear you well.
Okay, should I read it or you do?
All right, well, I can do this time maybe, since you did 2 times before. So how often do you encounter such situations where you are not sure about determining the buckling lengths that you need for your hand calculations, or you're not sure how to set the global model, the parameters, the supports, the links between in the nodes between the members and so on, right? So how often do you meet these uncertainties in your job? So never, occasionally, sometimes, yeah, or very often or daily. So the voting is in progress. All right, I see you voting. Janko.
Yes.
Question for you again.
Question from you. Okay.
Did you feel uncertainties? Did you feel did you meet situations where it was not simple to determine for buckling lengths in your practice?
Quite often, I can say. Yeah, the ideal situation of a simple supported beam with no ramifications, no weird circumstances, no strange connections coming in, it's quite rare. You can, you can face it as it's there, but the reality can be different, and mostly with some portal frames and multi-story steel structures. It's not that easy to identify what's the correct buckling length. You can try to help yourself with global models, but it's not that easy to figure it out because you have different kinds of loads coming in different directions. So it can happen quite often, yes.
Guys, can I chip in on that one?
Yes, please go on.
From my perspective, one of the hardest parts were when I was in consultancy was when we were doing strengthening of structures, where the behavior of an existing steel frame changes from one type of development to another type of development, and you needed to try and understand how the amendments to the existing frame with columns in different places, different load paths, different loading, different patterns of loading, how that changed the behavior of your analyzed member from one historical perspective to the new perspective. that for me would have changed the game. Member, we didn't have access to Member at the time, but now seeing what Member can do in that situation, it would make a massive difference to the way that we approach strengthening.
Yes, correct. Reconstructions, retrofits, yeah, it all makes sense. And for our listeners or our audience, it's not a weird stranger in the ether.
Yes,
it's our colleague, another product engineer, Ralph Pullinger.
That was Ralph, our other little helper today, rather hidden, answering your questions on the way of the webinar. All
Thank you,
right,
Ralph.
so let's see the results of the voting. I think everybody has already voted
at least once.
So let's
sharing the results.
Yeah. All right. We see that occasionally, sometimes our colleagues from practice meet this kind of expected answer. So thank you for this voting. And I will now pass presenter to Janko to conclude our webinar today, the whole session.
Okay, I try to make myself a presenter. I hope you can see it now. Probably not because of open poll. Still.
I have already closed it. So
Perfect.
you take the presenter and share the presentation. Yeah. Right, it's there.
Now I'm there. Okay, so some outcomes of today's session. Yeah, as I mentioned, if you work only with the simple supported beams, simple cantilevers with no other connections coming in, no other ramifications with loading, stiffeners, imperfections, and so on, you don't need our IDEA StatiCa Member tool. But if it's not the case always, if you have another connections coming in, another members, you don't know the stiffness of the connections, you have some geometrical nonlinearities or different cross sections, imperfections, that's where the added value is, and quite precise analysis can be done very quickly. The other advantage is visualization of the results. It's not only the numbers, it's not only spreadsheets or tables you are checking. You can see the behavior of the structure. You can see it in 3D scene. You can see it with colored rainbow colors of deflections and stresses around the connections, around the members. So yeah, you are not only calculating something, you can show to your clients what's the real behavior behind the structure. And the simplicity, as you could see, it's not that advanced UI. It's not hundreds of parameters you have to set. It's quite simple to set the basic geometry, set all the connections, load it somehow, and then evaluate which buckling shapes are dangerous, critical, and select what you need to analyze further. So at least these three added values, I think, the biggest benefits. And now some space also for other questions. We try to answer everything during the session, but we have also several quite interesting general ones. So Adam, which one do you see for majority?
In the meantime, I went through the questions. So I picked two, since we are also a bit over time. But thank you for your questions, by the way. And I will probably share my screen to show you and discuss the answers. So first question, there was, do you implement eccentricities of the perpendicular beams in global FEA software to avoid unbalanced forces in IDEA StatiCa? So the answer is yes. So if I go back to this FEA software model, the eccentricity of these bracings, you can see it visually that it's eccentrically input also you can see read the eccentricity value is 160 millimeters. So since you calculate this model, of course, that's something I didn't show. You can easily export this node into IDEA StatiCa checkbot, open it in connection, and have the data there. Of course, the forces are balanced. Since everything is correctly set in the global model, then the forces are balanced in the connection. You can see that in here and this tab here. So there are no unbalanced forces. All right. That was first question. And the second question, can you find the actual beta factor in IDEA? So if I go back, the beta factor is this. So the beta factor to determine the critical length for buckling calculation. So in Member, you actually don't find it here. This is the beta factor is used for the hand calculation, the analytical approach. You need it to determine the buckling length and to follow the equations procedure. In Member, this is all done by the solver, so you don't need this beta factor because the calculation is done different way using the finite elements model of these 2D shells. And so you totally skip this problematic part. This is all done for you inside, and you only see the results. So such simple it is. All right. So thank you for these questions. I hope I answer them enough. And so I now pass the presenter back to Janko.
Yes, thank you. Yes, and where you can move forward with learning of IDEA StatiCa tools. We have a platform, educational platform campus, where you can find several courses dedicated for steel structures and concrete structures as well, especially for the tool you've seen today, the Member app. That's the third course in the steel part. So please visit our campus webpage and you will find much more information about how it works, what's the theory behind. And what can you look forward next? In January, we are preparing the next webinar dedicated to parametric design using the Grasshopper. So very hot topic, which can be handy in this cold weather. And it's not the only webinar we planned for year 24. So you will find the next ones on our webpage and in your email inboxes. Yeah, what you will find after the webinar, there will be a short survey. Please go through it. We are really keen to know your feedback. The recording will be on our support center in the webinar section or our YouTube channel today or maybe tomorrow. You will get the link to this. And if you're interested in the tools you've seen today and you don't have the license yet, please get our trial version on our webpage and find much more information about how it works in our support center on webpage ideastatica.com. And with this, I would like to wish you a stress-free rest of the year, Merry Christmas, and yeah, stay tuned, and probably goodbye for this year. And Adams.
Yes, I wish you Merry Christmas. Wish you happiness and good luck with your projects. And see you some next time, and have some rest during the Christmas time. So goodbye.
Bye-bye.